Hi, my name is Josh Cherian, and this is Samantha Ray. We're PhD students at Texas A&M University, and we'll be presenting an active recognition system for taking medicine using in-the-wild data to promote medication adherence. It's estimated that nearly 50% of patients do not take medication as prescribed. These patients are subject to worsening clinical symptoms and outcomes, increased hospitalization and readmission rates, and increased morbidity and mortality rates. For the broader healthcare industry, it's estimated that $100–300 billion are spent annually in the United States on dealing with the consequences of the issue. Over the years, a number of solutions have been put forward to improve adherence rates. Solutions have included electronic medication packaging, or integrating sensors into medical containers, such as pill bottles, pill boxes, and blister packs. More commonly, there have been a number of mobile applications that have been developed, which have achieved varying levels of success. All of these solutions, however, are broad strokes. That is, they're not tailored to the individual user and their habits and lifestyle. Because of this, their utility remains limited. Human activity recognition, or the recognition of human activities through the analysis of wearable, inertial, or ambient sensor data, offers a means of facilitating this level of personalization that existing systems are lacking. Systems could leverage knowledge of when and how patients take their medication, in addition to context such as prescription information and medical history, to provide timely, personalized, and ultimately more effective interventions. Over the past 2 decades, research into activity recognition has shown that the combination of sensor data and machine learning techniques can be used to recognize a wide variety of ADLs, or activities of daily living, which are daily self-care activities. To our knowledge, no study has sought to recognize bacteria taking medication in an unconstrained real-world environment. So specifically in this work, we aim to do just that is extend the body of activity recognition literature to include accurate real-time recognition of the action of taking medication. More broadly, we hope to address one of the larger outstanding questions within the field of activity recognition. That is, can we develop an activity recognition system capable of recognizing ADLs in an unconstrained real-world environment? So I want to take a step back and talk about why this is difficult and how that's influenced what we could do and ultimately what we chose to do. Traditionally, activity recognition work has been based on data from controlled or semi-naturalistic data. This is problematic for real-world implementation of these systems, as usually in real life, individuals are doing activities other than their related activities. In other words, rejecting unknown activities is essential to the success of a practical implementation of an activity recognition system. In our user study, for example, which we'll go over shortly, over 99.5% of the data was labeled as an activity other than taking medication. Considering the problem is that the class of interest is rare, the natural next step would be to oversample taking medication to improve its representation in the dataset. However, oversampling the activity of taking medication runs the risk of creating a model in which incorrect understanding of the world. Unlike a classifier that detects spam versus legitimate emails, which focuses on 2 distinct classes, the activity of taking medication looks similar to other activities, most notably eating and drinking. A model that thinks you're taking medication every time you take a sip of water cannot be used in a real-world setting. To encourage precision of the minority class, instead we could undersample the majority class. The main issue there is that the majority class contains many activities, specifically every activity that is not taking medication. If you undersample, you need to maintain that richness so that the model has a clear idea of what those other activities look like, and they are not a weird variation of taking medication activity. On that note, the other main challenge of this domain is that there are many valid ways to take medication. People have different containers, use different hands for different tasks, and varying what order they do the tasks in. We explored the design of a user-independent model, but found that the generalization to unseen users was terrible, implying that users were not performing the activity in a similar enough way to correctly label the samples. We confirmed our suspicions by creating a TS&E visualization. The gray dots in this plot are activities other than taking medication, labeled nothing for short. Colorful dots are specific users' data for taking medication. As expected, taking medication is not distinct from other activities. However, there are only a few clusters, and participants are dispersed between them, meaning that participants were not consistent in how they performed the activity. For our study, we collected data from Polar M600 watches worn on both wrists. This data was transmitted to an Android smartphone app, which also facilitated the start and stop of data collection process and data labeling. For our study, we procured 9 participants. They were asked to collect data for about 1 day, although compliance to that varied, and label their activities. In particular, participants were asked to label 5 activities of interest: brushing teeth, drinking, eating, taking medication, and washing hands. For taking medication, participants who did not take medication naturally were provided with a pill bottle and M&Ms to serve as a placebo medication. We extracted 106 features from sliding windows of raw data. Chi-squared subset selection yielded 50 optimal features, which were fed into a control bagging classifier. Hyperparameters, so windows has window overlap, were returned using nested leave one subject out cross-validation and the tree-structured Parson estimator algorithm. Many of these features are commonly used in activity recognition. A few, though, have been adapted in the fields of speech recognition and eye tracking. We go over these equations in the paper if you would like more detail.
All that said, we devised a way to address the data skew while still using the entirety of the dataset to our advantage. For those who are unfamiliar, bagging is a randomized ensemble method that creates K classifiers on random samples of the data. Since this practice decreases the variation of the produced model, bagging generally would exacerbate the data skew problem, as many of these samples would only contain the majority class. An elegant solution to this problem is to enforce a data skew by sampling the minority and majority classes independently. This design results in multiple classifiers with different undersampled sets of the majority, creating multiple views of the world. We empirically determined that a skew of 2% to 10% works best as shown in this box plot. To create a more meaningful baseline for our model's performance than just random guessing or 0R, we trained a model for each participant in our dataset. The average of these macro F1 scores represents the expected performance of a user-dependent model. Throughout these experiments, our performance metric is the macro F1 score in contrast to the weighted F1 score, as the latter would not represent the performance on the minority class accurately. Notably, the performance has a wide range across users, implying that some of these users perform the activity more distinctly than others. Our first experiment of a user-dependent controlled bagging model did not reach our performance goal with only a macro F1 score of 0.721. We analyzed the results across the participants and found that some improved while others worsened. This outcome implies that having more data pulled the model away from some users, decreasing the recognition rate of the activity of taking medication overall. So we wanted to know if tuning the model back towards those specific users would increase performance by creating this user adaptive model. This practice simulates the system adapting and personalizing to a user over time in our envisioned medication adherence interface. But the same problem occurred. The control bagging model alone was not enough. So we turned to another machine learning technique to improve model performance, stacking. Specifically, we were inspired by the idea that if the model fails in a consistent pattern, that a second model should be able to decode those errors. We call this vector of the C times K prediction probabilities a portfolio as a shorthand, where C is the number of classes and K is the number of classifiers within the ensemble method. We explored heuristic-based methods such as similarity and using another classifier as the secondary model. With another phase added to the classification pipeline, we updated our baseline accordingly, raising it from 0.735 to 0.771 based off the best performing method. The best performing methods were cosine similarity, Manhattan distance, the SVM classifier, the multi-layer perceptron classifier, or MLP for short, and they're given in this table. Unfortunately and unexpectedly, the user-dependent model did worse than in the first experiment. However, the fact that the similarity-based methods did the best pointed to the reason behind the performance drop being the variation across users. Those methods aren't as impacted by the exact values of the prediction probabilities, making them more robust against poor generalization. So we asked the tuning question again from experiment 1. This time, performance did improve over the baseline. Our highest baseline was barely surpassed, but each explored method saw an improvement. The main takeaway from these results is that the classification system for taking medication requires careful tuning to preserve the expressiveness of the data while maintaining precision. Recognizing a relatively subtle activity like taking medication from in the wild data is a difficult task. The progress shared in this work demonstrates the first steps to developing a user-independent model that would empower medication adherence interfaces. We envision a system that functions as a personal health assistant, reducing the mental load associated with medication adherence, and aiding the maintenance of one's health by reminding its user to take medication and automatically logging when they do. These are our references. Thank you very much for listening. We also want to plug our research lab, the Sketch Recognition Lab at Texas A&M University, which focuses on developing intelligent user interfaces for applications such as education and health. Thank you again.